Okay, I start a timer here. First of all, thank the organizers, the postdocs and the graduate students. They are very enthusiastic, organizing this workshop. It's the first one. I remember we talked last year to have one because it's an urgent need. So today I will introduce some work of joint video and text parsing for query answering. I will show some demos that is supported by DARPA on the so-called restricted Turing test for scene and event understanding. Since this is the outline of the presentation, I will first try to put a few motivations for why we have a vision plus a language. And then I will show you a running through example of joint text video parsing and answer the 5W queries stuff and the Turing test. And then finally, I will talk a little bit about the communicative learning as a future work, ongoing work. So since my talk is the first, I'll just bother to show a few facts that motivate this integration. So vision and language are tightly coupled in the brain, obviously. The first striking phenomenon people found in the 70s was this McGurk effect. If you haven't seen this, go to the YouTube video, search McGurk effect. So it says that if you look at the picture, the person talk like a da, ba, that kind of thing. And then if you don't look at the picture, and then you hear one thing, and then if you look at the picture without hearing sound, you perceive one sound. And then if you put together, you got a third one. So that means the vision, like lip reading and speech recognition, has been integrated in a very early stage in the phonics and syllabus level. So that is quite striking evidence. The other things, obviously, I just found this picture. There are many others, of course. When the cortical areas, of course, all the brain areas is complexly connected. So when people, for example, when you see an object, you have certain areas lighted up. But when you hear someone talk about it, right, say hammer, the words, you hear the words, then similar areas will light up, there's an overlap. That means some of the vision areas kind of evoked. When you hear the sound, like someone next door, pounding with the hammer, you also get some words, areas light up, overlap with vision. So that means, if we want to do vision right, we got to connect with language as humans do. The second reason is that vision and language they supervise each other as an individual person, like the babies when they grow up, right? So they see things, they hear something, the two channels really supervise each other in a certain way. Everything, if you count the vision and language all together, everything should be unsupervised learning, right? Because if you put a total input to you, right, as a total sensory input, the vision you heard, you see, visualize, supervise the language to ground, say this is the object, or that's the scene, then you got it. And then the language will convey some hidden variables, hidden semantics that is invisible, like a name, attributes of certain relations or function, or causality. Those I usually call them the dark matter and dark energy in the computer vision because they are not visible in the images. They got it from the language, so they supervise each other. And then the whole learning should be totally unsupervised learning. Okay, if you put it into the loop. The third part, is a quite interesting branch of research. It's about joint visual and verbal communication. In all communications, like TV news, advertising, political campaigns, social media, people communicate with each other through both the verbals, like text, and then also the visual stuff. So this is so-called, persuasion. I was surprised to know that a few years ago there was a department of communications. I thought they're doing computer little work, but actually not. It's journalism. They have many years of research, textbooks, talk about how the journalists, to select pictures, how they shoot a picture from a certain angle, camera, how to what kind of things put it on the background, so that it make it look right, so they can persuade people. Of course, people doing commercial stuff like this. This is the Mac commercial in the, I think it's in the 80s. So it give you, they didn't say anything, they just put a picture and get it into your memory. And then there's a political campaign for Obama, his sleeves goes, what's up, and it means he's working and smiling, he really care about education. This is an issue of so-called, visual persuasion. The student, John Salk, a student of mine, he published a paper last year, and actually he got a tenure track position at UCLA this year. It's just one CVPR paper. In the Department of Communications, this is social science, because a lot of social scientists, they want to analyze all these events going on in the internet, social media, and so on and so forth. Usually they only analyze text. But now they want to analyze vision, the images and with text together, because this is all subtle stuff going on. So it's a big new direction for people if you are interested. Obviously, this number 4 motivation is that we want to scale up the evaluation. Nowadays, you have evaluation by just bounding box, the classification. But when you go to a high-level vision or AI type of recognition, those become a little too low level. People now begin to talk about a scale up the learning and evaluation process by close the loop, as humans do, as we said. So this is one of the paper published by Don Gieman this year. They propose this so-called restriction tuning test. We are in the same DARPA project. They designed this test, but they didn't go through the test. But we go through the test. We went through the test for us. So basically, they want to design a storyline. So give you a picture or a video, and they say, well, give you a spot. You just point there. Okay, is that person? Is there a person in this region or in that spot? Right? And then, and then if you say yes, and then they keep asking, is this person, how old they are, what kind of person we're talking to each other? Just keep going. They give you a yes and no kind of queries. I believe that in the future, or when the low-level vision detection become more reliable, people will have to evaluate. Not ground truth by people labeling anymore. Just ask you questions, and whether you get it. That's pretty straightforward and high-level recognition problem. Okay, so that's the motivation, at least from my perspective. Now I just give you a running through example of this joint video text parsing. I know recently people doing neural work for this kind of work, but I do it in a old-fashioned way using grammar. So suppose you have input. This is a surveillance video, video intelligence, so-called. Then sometimes you have a so-called human intelligence. Some people just input into the text, and report certain events. For example, this is a text input, say a silver SUV. Then we passed both using grammar. This is the video grammar. I will talk about it. And then shell stack is this is the event. The car approaching, stopped, and driving away. It's a vehicle, and then there's the building detected over time. And here is the we use the Stanford language parser. Basically it's the basic stuff. And then you transfer those relations into a parse graph structure. So this say someone stopped, and there's the agent, is SUV stopped, and then the person, I didn't mention that actually. The person actually. So they just say SUV take a picture and of that federal building. So now you know that building is a federal building. So when you put it together, we want to find the common parts. So the shadows overlaps shows that there are some common parts, and then you try to extend from there. So you have a joint parsing process. So this is a example. I will show you how we do it. So before we do this, we should have a representation. The representation that my lab has been studied in the last 10 years, probably more than 10 years. A so-called spatial, temporal, and causal NOR graph. The NOR graph is basically a probabilistic graphic representation for stochastic, context-sensitive grammar. The N nodes means that you have decomposition into parts, and then all nodes means you have alternative choices. And then you have links at many levels to show the context. But we have three dimensions. The spatial dimension says that suppose let's look at one object. Is this the pointer? Oh no. We have one object O, and then it will decompose into some parts. And then you have parent nodes. So this is the hierarchy. And then you can terminate a ground with some sort of image templates or features to the images that you observed. But this object usually can participate, like affordance link, participate in a number of actions. That means like a cup or a hammer, or those objects they have involved in many those actions in the thank you in the temporal NOR graph. And then they also have this causal, means that each of the object has a so-called we call fluence. It's a change in status, like lights turned on, turned off. This enough, yeah. Okay. The lights turned on, the door is closed, or the cup is filled with water, and so on and so forth. So this is fluence. The object has fluence, the change in status, like cell phone ringing, and involves action, and this is the visual aspects. Then for each of the action, if you look at action, they also decompose into parts, right? At high-level events, in time, that each step has multiple steps, and then you can further decompose. And then usually action would be terminated as a certain spatial relations between objects and agents, like a grasp or a cup or something. And then the actions also have some causal effects to change the fluence from 1 to 2 and so on. So we have workshop downstairs talk about vision cognition. That is talk about this kind of causality and so on. So then the third part is causal. Causal aspects means that you do something, and this action causes the fluence to change. Like the door is open, you can have several ways to open the door, and each way will further goes, So the nodes are kind of connected in those multiple dimensions in this spatial temporal NOR graph. That's how we represent things. And then when we try to parse the events, they're all connected so that we can do deductions jointly through this spatial temporal NOR graph stuff. So okay, let me just show you a running example as we go. The picture here is I thought it was, this is just a picture, not a video. So some people are lying in front of this food truck, waiting. And the input text could be, we just ask people to input some text descriptions. Some people make it short, some people make it long, like people buying food at a food truck, or people, this is a food truck. So the vision part, we're doing some group activity analysis with Selisa, actually. This is published in ECV 12. So we have group activity, individual actions, people, and so on. So you generate some sort of a partial. This is only two groups here. The other part is not tracked for clarity. So then the video parsing shows that, okay, you have a human waiting there, but they don't know what it's doing, what is going on, because semantically, you don't know this is a food truck, actually. It's hard to detect this is a food truck, Then you also don't know what this is going. The people are just standing there, or standing or waiting, agents. And then if you have text output, let's say people are buying food at a food truck, this is how the language parser will give to us. Buying as an action, and then there's the agents that, we at the food truck, and then, patient with food. Also agents with humans. So you have a graph representation. All here, we just have simple nodes. Okay. So this paper was published this year in the IEEE Multimedia Joint Parsing. So now the goal is to have a joint parse graph in the following way. So that is, the video input, we have a parse graph, right? You just go to the video, explain the video, and then the text, you have a parse graph, explain the text. Obviously, there's something common. And then you want to join them to develop this joint path graph, PG joint. Okay, so this joint path graph video, and then through maximizing the posterior probability distribution, that if you have a joint and then you have this likelihood, and this goes through the likelihood. Okay, and then you have a prior probability. That prior probability is defined on the all possible path graphs in that spatial, temporal, and causal NR graph space. So basically, each path graph will be like a realization that derived from the grammar. So it's as an instance. So the grammar defines this probability. Okay. So when we compute, if you have this path graph PG from, let's say, this is the path graph for the visual part, and then you have for the text language part. And then the first thing is that we want to find the common aspects, which could be very challenging because that depends on the tasks that we're working on. Let me just show you that this is the 3 levels of complexity. For example, in the surveillance video, I showed you it was easy because you just say, well, what are events happening in that time with this text description. You ask people to describe it. They are tightly coupled, so you're going to find some pretty good overlap between the 2 path graphs. The second one is a little harder. This one is recorded from news. The news captain says that more people are losing jobs and moving out of town. Then you see this woman is doing, what is doing? Packing, right? Yeah. So it's packing, so it's moving all the stuff, in the kitchen, just get out. Okay. So that is the news. You can see that, this loose job, move out of a room, there's nothing common with this. But you have to, using your imagination to deduct from both video and the text, and then you find the common part. Okay. Humans are pretty good at doing that, because we have this prior knowledge built it up around this moving, losing job, and then just in the packing or some people doing. So the third one is even harder. This is more abstract in the news. Say the crisis escalated over the past week. This is the United Nations, obviously. You see this is the council. And how do you, link those? I don't know, actually. So that remains to a challenge of high level, learning. That means when you learn vision language, a lot of semantic meanings are associated, are defined with social events in the text, in the object. Like when you see a rabbit, you say, oh, that's Easter. And it's all through this. Now, what we need is that, you correct certain things, you found a joint one. This is a correction. That means something wrong, that's ambiguity, disambiguate. And then you want to correct certain points, like the SUV, take a picture. That is not an SUV, probably it's a person, take a picture. That kind of thing. And then finally, you also want to do a deduction. This is hard. Because as we know that these 2 circles may not overlap, they may totally disjoint. You have to grow both circles so that you find a common part, and then you derive from there. Let's go back to that running example I just talked about. So you see there was a lot of people waiting in front of a food truck, and then the text said there was a food truck. Let's suppose that we just have these 2 input path graph, okay? And then we try to see how we can derive from this framework. So basically, the first thing is that, this video parsing, the text parsing, the first thing is that, okay, waiting for what, right? It's a part of the action of, there's a parent nodes from a temporal NR graph. Say, people wait, you want to see typically what do people wait for, right? This is an event, there's some other actions. Okay, let's potentially a prediction, So let's try to grow one step in this mosaic, like a mosaic growth. And of course, there are many other choices along the way. We just go to one that works. And then a food truck, you're going to see, okay, this food truck has some affordance. Means what people can do with food trucks. Okay, they buy food, with people buying food. So this is maybe a note as you got that from the action graph as well, linked through this affordance map, affordance link. So, and As we go, of course, the likelihood is going down, but the prior is going up, okay, to make this event. And then you notice people buying the food could be, this is all dark, in a sense, people reasoning. You buying the food, maybe, suppose the buying process involves waiting and ordering, and then you leave, like the process. And then further, you can say the ordering change the fluence, actually. The humans also have fluence, like has food, or hungry, or, are thirsty. This human has some sort of fluence, like a mind, okay? And then that change over time. When you order, you got it, and then this thing change. That's the causal graph, the causal aspects when you put it. So you can keep going, and then once you get to this step, you will find this subgraph. Some subgraph will overlap. This is what I just drawn here. And then now you got it. To merge these two aspects together into one common one after some graph editing. All right. And then you further going on. This is the second agent. You're doing the same process, the multiple agents. Okay. So the process can go on. That means the person will have a mind. A mind, I use a pentagon to represent the person has a mind. It's kind of a fluence, social fluence. Hungry, or will be, next you can predict, well, what are they going to do? They're going to take the food away and then they eat lunch or something. So obviously we can keep imagine until I become daydreaming. Okay, that you have a stop criterion that this is imperceptible in the sense that when you try to further derive the entropy, that means the too many all nodes you can go. The entropy is uniform. The entropy is high because the all nodes are a uniform distribution. Therefore, you stop as a criterion. So I didn't go through all those examples, the details on the formulation, but it just roughly is usual stuff that you're familiar with. So that means the likelihood will define a number of the energy, based on match, the match and the correction. So you define a semantic distance, like a SUV and a vehicle, right? That kind of a word net. And then you have a temporal some sort of relations, and also the time, the text showed up with the events, alignment, and the spatial distance we talked about. And then priors, this one we post all the grammar, the grammar into this kind of a similar like the Markov network, but it's a little involved with the hierarchy, here. So we have this all kind of relations, spatial, temporal, or causal relations. If it happens, then you have certain ways, and then you try to learn it. So the evaluation was done by a text generation. So after we got the joint parsing, we generated new text descriptions, and then we match that with human text description, and then see how well they do based on that. So I'm not going to talk about those issues. I would go straight to the third part. How do we answer the 5W kind of queries? So this is a DARPA project started a few years ago. They define ontology on, say, objects, indoor, outdoor, buildings, grounds, chairs in the room, and then humans, the parts, clothing, and the small objects like pizza, books, balls, appliance, and then behave, just action, basically. Actions or human actions, homing relations. Like this is the same object, that is a part of that. And then 3D, like occlusion, touch, and then clear line of sight. Like, does this person see that person? Does that car can face that, object? So on. They have a motion group activities, most attributes. Lately, we added more stuff as we go with robotics, like tools and intents, people's intents, so on. So we define a ontology so that you can ask any questions inside this ontology using this who, where, when, where, or why kind of thing. I will just show you one demo that we made, last year, a year ago. That was we started with this, simple running example. Then we extend to the more challenging examples in the DARPA project. So suppose you just saw, a single image. You construct 3D based on the reasoning. At the beginning, you only see a little spatial parsing. A lot of objects are missing. For example, you don't know what this is: the button, the elevator door, the trash can. But this is spatial parsing. This is temporal parsing. Temporal means the events. Each of the dimensions is like an event, someone doing certain things, multiple steps. This is the fluence, like the light is turned on, the door is open, the elevator door is open, or people drink. The change of fluence, this is change of fluence here. So the status change, the causal aspects. Then you can see that this also object has fluence. This is some keep monitoring the status. All right, as people perform more actions in this thing, like drink. At the beginning, it does not know what this is, and after see people drink, then you realize, oh, this is an object that was water. So, and then here we also have some text input here. Occasionally there was a student input some text, like the person's name, what he does. Then the text parsing is this, this person doing something, and then we jointly passed, into this joint spatial temporal parse graph representation. And then from there, from that joint parsing, we generate a text, more comprehensive text description. It's funny that we found out that humans describe things and very different from machines. Machines give you a lot of garbage details. Say, well, this time this guy he did this, he did that. A lot of steps tell you that humans just talk about a very high level semantics. So we ask people to make descriptions at 3 levels of details. At the beginning, you just tell something, general. Say 1 sentence description, and then you put a 3 sentence, and then you have 5 sentences. You just give them multiple details and see what do they say about a picture, and then and label, and compare with the input. So that is an example. Now, this is a YouTube video. You can find on YouTube. So then we can answer. We put all those things into parse graph. This is all a parse graph. So then you will say, well, what are people doing? This is all a returning all a parse graph. And then you click one of the parse graph is here. So here, say he talks. You just click this person. He was talking to the phone actually. And then this is the query. What are people doing at the fountain? Okay, this is the fountain. This is a 4 events involve this fountain. Okay, he bent down. That means here's the fountain. He bent down. That was an action. Then legs was drink. So when did he drink? He drinks from this time. Of course, that's easy. Where is just the bunny box. So when you answer, so why does he drink? He drank because he was thirsty. That's just a you have 2 kind of whys. Why? First, you can answer based on the fluence or his mind. Then also you can answer based on, say, what he's going to do next, because he drink because I want to do something. So drop the trash. So this, you have different parse graph aspects that will give you the different type of answer. Okay, so now we scale up. Oh, phase 3 actually, now it's phase 4. So we have a DARPA test. I remember the Don Giman paper I showed you at the beginning. They designed, okay, let's evaluate it in an AI way of computer vision. So how many time I have? Okay, I'm okay. So we have this indoor, outdoor cameras, the highly independent company, as a third party, to evaluate us. So basically, this is SUT, which is a system under test. This is a military, kind of name. That's what we developed. And then this is what the company developed. This is BAE Systems. They have a demo GUI, and then with this evaluation interface, talks through us through internet. So basically, they ask all the questions, whatever they want to ask. And then we have the answer online. So the problem was like they recorded, the first time they recorded like 1 terabyte of video, and then next time more. Actually, we just tested it last, a month ago, 2 months now. They just shipped the video to us. We parsed it, all the parse graph as we promised. Given we parsed actually 2 weeks of time. it's intensive. We just all the whole lab, stopped. We put all the computer together with cluster. And then when the time stops, and then we begin to ask questions. So some of the queries are like this. Basically, they can pick up a point. You just say, what is this? What is this? Is you say this is a person. Okay. Then just mark it. Then we define this person. Oh, that's an animal. So after a while, they define a number of those objects and the persons and the vehicles, and then they began to show that what are these questions? Like who does this? Oh, and then as we said, answer those queries. They have both polar queries, yes, no, and non-polar queries. So I forgot to show you the demo first. Let me quickly run a demo on my desktop. So this is some of the videos. What? Wait a minute. It was run yesterday. Hey, it was all fine. Why you wanna? Okay, so here's what? It's like four of the videos. They have people activities. They just pretend to do, a lot of people they hide, to do activities, play baseball. Small objects is very hard to track actually. So now we construct a 3D dimensional representation of the people. They can ask you what kind of behave, what kind of 3D relations. This is the field of view of each camera, of these four cameras here. So they have bicycle running through. Then they can ask, whether this person doing certain things. Okay, this is one, actually. This is a lot of crazy stuff going on because they want to be crazy. Let's stop her. And another video I show you was parking lot. This is outdoor. They have indoor. They have 5 areas. So they have moving camera. So the moving camera is moving on top of the car. This is the field of view online computed. We on top of this Google Earth, Google Map. Okay. So they tell us roughly we have GPS signals, and then we construct the 3D roughly, and then show objects moving around, and then you can see that this camera sees some new cars here, which is only this camera see, and then the other camera does not. And then they ask funny questions, like AI type of questions. They have a bicycle running through. They just say, well, during that space of time, is anybody, his feet is always above the ground. That's kind of questions. Okay, very quickly. So this is in a phase 2 test. They ask a question like this: in this room with 32 minutes, is there at least a chair in the conference room no one's ever sit in? Actually, this is a chair actually here. No one ever sit. You have to check all the people around, to see a chair not being sit. The answer would be yes. It's a person putting food in the mouth. This is, during that time, And then it's the upper no leg of that person with a white shirt, occluded from the camera by the table. So this is the person. Things like that. And then you have also things like this is all the events. Say how many people are in this spatial scene. So you have to count like more than 2 people because you see 2 people, but there's a driver here. The guy was coming from the passenger seat. There's more than 3 people. And then is a yellow person. So let's tell you how they do it. Then the indoor scene. This is what we did 2 months ago. We have 100 questions for this area. So total is more than 1,000 questions. And ask we can choose no response. We just say we don't know. Actually, we don't want to talk about it. Just 29. So that means we choose not to answer, not to deal with it. And then for the one we deal with it, we got got a 78%. Anyway, so I'll just quickly go through the future work. So I think in the future, we're going to talk about this situated visual and verbal communications. There's a lot of psychology studies, origin of human communication, very interesting, how people, animals got it, this infrastructure. Basically, the infrastructure that we want is you have a shared knowledge, and then, which is an NOR graph, the spatial temporal in my language. You have a situation which is a partial pass graph at a certain time. That means when we communicate with robots, for example, at a time you have this partial pass graph. That means at time t to now. Okay, that's what we understand. And then you have some intended plan. This is what we intend to do, this is going forward. And then this is attention. That's what we're talking about right now. Okay, so we have this representation in a graphic way. Then we will talk to people. You have different minds, actually. The robot has different ways of understanding. You have confirm. I think people, Joyce Chai here in afternoon, and Stephanie, I believe you guys are going to talk about it. Yeah, this is not slides. So then, wait a minute. I was sort of going to show a demo on robots learning. So we have a lot of this people folding clothes online, and then didn't run. Okay, fine. So then people talk about it. How do I do this on the YouTube videos? And think. Then you build this spatial temporal NOR graph, causal NOR graph, through the learning process. And then from there, actually, we reach the full autonomy. Like the robots can do this. We join to this with the work with SRI. So basically, you have a path graph as a plan coming from the robots, coming from the NOR graph. Then you just automatically doing it. All right. So I'm right on time. Motivation, why we want to be here. I hope that this community will grow to bigger, and then I feel this is the future because vision to scale up has to go with language. Otherwise, it's really hard. And the future will be communicative learning in the sense that you're just learning by talking so that everything is totally unsupervised, supervise each other. Okay.